will run in some things, but we wouldn't use it to run an electronic circuit. But what we're doing is we're working on the makeup of a power supply. And of course, to start off with, we've got to have, we're looking at what we call a linear power supply. Linear power supplies are the easiest to fix when they break. They're the easiest to design if you wanted to build your own power supply. Switching power supplies, we'll get a little introduction into those. Normally, switching power supplies are they're a little cheaper. They're more efficient, but if they break, you just can't fix them because of the complication of the circuit that's required to regulate a switching power supply. The linear power supplies, these are pretty neat. And they're still around a lot of different places. Another problem we have with switching power supplies is they create a lot of noise in your in the power grid. Create phase shifts, which is not good. So let me bring up a PowerPoint. And we'll start off, so we started off with looking at a basic linear power supply, right? And we start off with a watt. Of course, we've got to have a source of our power, so they put a plug there. And we have a rectifier. What's the function of the rectifier? Yeah, but what we say, it converts AC into what we call pulsating DC. And then we're going to, after we do with this, we're going to figure out how to add a filter. And the filter is going to take the pulsating DC and convert it into what we call unregulated DC. Which is, what does that mean? Varies with load. Y'all understand that? Also, it varies with the input. So if my input voltage goes down, the output would go down. If my input voltage goes up, the output would go up. If I put a higher current load on it, the output would go down. If I take a current load away, the output would go up. So this is what we call unregulated. And then eventually we're going to add a regulator. So a regulator would give us a constant output even with those conditions that we talked about. So if I didn't plug it into the same wall outlet, you know, you can go at home and measure your outlet, and you can come here to the college and measure these outlets, and odds are they're not going to be the same. So if the output voltage was dependent on a ratio on a transformer, then you would get a different output voltage every time you plug it in, depending on the outlet you plug it in, right? Does that make sense? And that's what we'll get on these power supplies. So this is what we're working toward right here. And right now we're right here at this section right there. And we looked at half wave, we looked at full wave, and then the last thing we looked at was what we call a full wave bridge, which consists of 4 diodes. So a full wave center tap consists of 2 diodes. Then a full wave bridge consists of 4 diodes. So this is a full wave bridge. And this is where we left off at. And then, of course, what I did is these things are so common that we can get them integrated. Half wave is too. It's pretty neat. They'll look like a transistor. Full wave center tap is common too, but they'll look like what we call a transistor, but they're not. So you be careful. So if you see a three-legged device in a circuit board, it does not mean it's a transistor. It could be what? It could be a 2-diode arrangement for a full wave center tap type thing, which is very popular in switching power supply. So what I used the other day is, sorry, I didn't bring up my camera application, is I use this 4-way bridge. We're going to replace it tonight. And, so this is an integrated circuit where they take the 4 diodes and integrate it into a single package. And then 2 of the leads are marked what? No, I'm in the center. I'm sorry, AC. So that's where we bring AC. There's not a plus and minus there because AC has no polarity, right? And then this would be the output of the bridge right here. One of them's marked what? Yeah, and the other one's marked plus. And you can get these different categories. We got a 25 amp I'll show y'all. So you can get these integrated bridges, different amperage rating. Of course, the smaller the amperage rating, the smaller the bridge will be. What we're going to do now, though, is we're going to hook up 4 diodes in a bridge. The bridge, and you see this thing drawn different ways, and the problem is when you're new to electronics, what people try to do when they hook up a circuit is they try to hook it up the way it looks on the schematic. And when you get into the real world, you're going to find out that the schematic and the way it looks on a printed circuit board are entirely different. What we're doing on a printed circuit board is we're trying to get the components laid out for number one, where we don't have any crossing wires, right? If I have crossing wires, that means we got to go to a layered board, or we got to put jumpers on there. And we're trying to occupy a smallest amount of space that we can possibly occupy on the circuit board. So that means these guys are going to be laid out all over the place. So another popular way of drawing a full-wave rectifier, and this will work good for 3-phase. Full-wave bridge rectifiers for 3-phase are basically impossible the way we draw it the other way anyway. So another popular way, and it's real easy, so you come up here and you got to figure out, okay, which way do I want to turn my diode? So if I come over here and draw it as a bridge, and then I'll come up here and I'm going to put my AC in right here. And then I'm going to take my DC out right here. I'm going to loop it even though that's not legal. Okay, let's say I wanted a minus DC. How are we going to turn those? How are we going to turn those diodes? So we'll make this one common. Well, first of all, when my AC has to see an anode and a cathode. Now, these diodes right here, these 2 diodes right here determine the polarity of the output. So if I want a minus output, I'm going to come over here and I'm going to point the cathodes back toward the source. See, now I got a short circuit there. I'm going to point the cathode. I got a short circuit. I'm going to point the cathodes back toward the source. So here's my source. I'm going to point the cathodes back toward the source. You see what I'm talking about? And that's the way we identify the supplies. What the AC has to do, it has to see an anode and a cathode. So what that means is I've got a positive ground, right? You understand? So this are common. So these guys right here, I'm going to point the anodes back to the source. So my AC sees a what? My AC sees a cathode and an anode. Down here, what does my AC see? It sees a cathode and an anode. The top wire determines the polarity. So I wanted a negative power supply, so I have the cathode pointing back to the source. My common is going to be positive, so I've got the anode pointing back to the source. You understand that? And it takes a little while to figure out the way those diodes go if I draw it like that. Another way that's very popular to draw it is to come over here and just put 2 straight lines. And then over here, I'm going to come over here. I want a negative. I would put the cathode back toward here. And then I come down here and I point these in the same direction. This right here would be my DC out. And my AC comes in right there. And that's the same thing. These two are exactly the same. Which one's easier to draw? Well, to me, these are easier to draw. And if I wanted to do 3-phase, I would come over here and I would just add another set of diodes. And then I would bring in the 3rd phase. And there's a 3-phase bridge rectifier. That's all there is to it. Try to do 3-phase with that, you just can't figure it out, right? Does that make sense? So if I wanted a positive power supply, what would I do? 2-phase. I would come over here and I would put my anodes toward the source, right? And then I just draw these guys in the same direction. They're both pointing in the same direction. And my AC comes in here. And then my DC would be right there. course, legally we're supposed to fill these in. And now this is a positive full wave bridge power supply. And my AC would come in where? Right there. Well, you'll see people trying to wire them up on a breadboard. They try to wire them up like this. When in actuality, this is the easiest way to wire them up on a breadboard. So I'm going to wire up a full wave bridge and actually wire it up using diodes. So I'm going to take out my bridge rectifier. Okay, make sure my power supply is turned off. Okay. Here's my AC right here. Probably have to shift it around a little bit. So what I'm going to do is I'm going to come over here and I drop one of my diodes. What do we want? Do we want a negative supply or a positive supply? Okay, so let's make a positive supply. It really don't make any difference. It's where you hook your power supply leads at. So I'm going to come over here and I'm going to take these. Okay, do this. I'm going to take the other one and do this. So notice they're what? They're pointed in the same direction. Can y'all see that? Okay. Then I'm going to come over here. I'm going to take the anodes. I'm going to connect those together. But notice my center, where the AC connects, I'm going to a different slot, to a different vertical line. Because I don't want where the AC connects, I don't want those spots connected together. Oops, I'll put that one in backwards. Now, of course, you're going to have to be careful with this because if we have these mounted on a printed circuit board, these leads are not long enough to touch together. But in this situation right here, I might get them parallel to fine. Is that if you accidentally push one of these things over, you're going to have a short circuit, right? You understand what I'm saying? So all I have to do is just point all these guys in the same direction. So I got the anodes connected together right here. I got the cathodes connected, and my anode-cathode junction are not connected. Y'all see that? Everybody okay? I've already got it, I think. I'm going to bring my AC, and I'm going to put it, this is not connected. I'm going to bring my AC over and put it at my junction between my two sides. And now we have our AC. Now, if I want, this is positive over here because my anodes are pointing down the source. This would be negative on this side. So what we're saying on a full wave bridge, right? Y'all understand? What we'll do is make one of these sides common. So when I come up here and take my oscilloscope and hook it up, this will establish the common side. So I've made the negative side common. This right here is going to be positive, and we need to hook this up to a load. Power supplies don't like to work real well if they're not hooked up to a load. That's what they're designed to do, is run a load, right? Oh, I didn't want to take that off. So I'll need a common. I'm going to hook this up to the common side. And then we'll hook this side up to the positive side. And hopefully when we turn this on, double check my work. AC goes right here. So my two ACs come in. I've got this one going to an anode cathode. I got this one going to an anode cathode. This is going to be my common side. This is where I put my black lead of my oscilloscope, which is grounded. This is going to be the hot side right here, or not the hot side. This is going to be the positive side. Diodes are connected together. Come on, folks. Now, let me turn it off. And this transformer hums. I don't know what it is about it. Just... Oh, I didn't have a load. Well, there's our full wave rectifier. We made it positive. How would I do? What would I do to make it negative? Huh? Well, no. You don't even have to turn the diodes over the way. You just hook it up the other way. You understand? It's just like the bridge that I showed y'all. Did I pass this around? They're labeled negative and positive. It's up to you how you connect the load. On a full wave bridge, it's up to you how you connect the load. Now, on a half wave, you have to do what? You have to turn the diode around. On a full wave center tap, you have to turn both diodes around because it runs a common. Here, the common is on the other side. So the circuit itself, the load itself establishes what's common, not the bridge rectifier. The bridge rectifier could care less. So if I want on this guy, if I wanted a negative power supply, I would make the positive common, right? You understand? And hook my load up to the negative side. If I wanted a positive power supply, I would make my negative common and hook my load up to between the common and the other. So what's nice about a bridge rectifier is that if you go from a negative supply to a positive supply, all you got to do is just change the way what you consider to be what? Common. I didn't even change the load. Of course, if you got a load that's polarized that needs a certain polarity, you might have to turn the load around. But there's really, so all I did was move my common over to this side and move my scope over to that, and then of course now we got a positive power supply. Now of course it appears to be snaking across there on my scope because my scope is not synchronized with the input signal. So to synchronize the scope, we use what we call the trigger. So this knob right here, it says trigger, and then there'll be a little white line that I'll turn, and as soon as I get it down inside the waveform, oh, and you gotta figure out which channel you want to trigger on. So I'm gonna bring up, so triggering on channel 2. Synchronize my scope to channel 1. There we go. And I'll turn the menu back off. So now it's synchronized. So when you synchronize your scope, first of all you got to do is you got to say, what do I want to synchronize it with? So when I bring up the trigger menu, which is that, and then this says my source, my source, and this is channel 1. If you switch it over to channel 2, it's going to go out of sync, right? Does that make sense? And it'll start snaking across. So yeah, all I got to do, I want a positive supply, I'll just come over here and switch this around. And now it's positive supply. Now the scope is out of sync. So what I do is just move that little white line until it gets up, and now it's got something to synchronize. And that's a full wave bridge. Now another thing, and this is a circuit that's really used a lot. Did you hear the? Yeah. It just started to do that the other night. Another circuit that we use a lot. It looks like a bridge, but it's not a bridge. So what I'm going to do now is I'm going to bring up the actual schematic for the trainer. Hopefully this is on Blackboard, but if it's not, I'll put it up there. And what we're doing is we're looking for the power supplies. I'll say handouts. Oops. Huh. Oh, here it is. So this is the trainer that y'all are using. This is the little booklet that comes with it. And all we're doing now is looking for the power supplies. Let's see if I got a PowerPoint where I've rotated these around. That's the digital circuit. This might be right. Here's the, yeah, it is. So here's the power supply circuit. So over here, what's that? I'm sorry, what's this? What type of transformer is this? Yeah, they're all step down, but what type of step down transformer is this? We have multi-winding transformers. We have tap transformers, right? You'll understand. We could tap the primary. The primary is not tapped. It's not a tap primary. But this is a multi-winding transformer. So we have 1, 2, 3 secondaries on this. But what we're doing is we're looking at this secondary right here. So this is a multi-winding transformer. Well, what type of secondary is that? It's our second full wave. It's our first full wave power supply that we looked at. What type of transformer is that? And I can't find my where I can get to my. I can do this. Let's see. Yeah, this guy here draws pretty big, so PDF will come back out. Yeah, I got to get out of the drawing thing. What I got to do. Still won't come back out. So this right here is a center tap transformer. But what is that? It looks like a bridge rectifier. That's exactly what it is. But it's not acting like a bridge rectifier. It's acting like two nodes. It's a full wave center tap. So what we do is, what we're noticing here is that the common is right here. There is no common on the right hand side of the bridge rectifier. So these guys here, we have two diodes pointing toward this guy. Down here we have these two diodes pointing toward this guy, right? Does that make sense? So this is these are two full wave center tap power supplies. But they're actually using a bridge, an integrated bridge rectifier to get those. So this is actually integrated inside a package. Can y'all see what I'm talking about? Yes or no? So when I do a bridge, one side of the bridge is going to be common. Here, when I look at the bridge, neither side is what? Common. Where's the common established by? The common is established by this center tap transformer right here. So this is common to these two. See the common right there, or the ground? These are common to these two. Well, so these two diodes are giving us a negative power supply. These two diodes are giving us a positive power supply. These we haven't got to yet. So here's our transformer. Here's Alabama Power, right? You understand. Here's the switch that we turn the power on. This is that neon bulb inside the switch that comes on when you do what? When you turn it on. Neon bulbs work off of AC. Well, they work off DC, but they'll only glow on one side. They'll glow on both sides if you put A on. And we put about 70 volts on it. So that's the purpose of that resistor right there, to do what? To drop the difference between the 70 volts and the 120 volts. Here's my center tap transformer. There's my transformer. Here's my watt. There's my rectifier. So this is where we're at right here. And these are two. What they're doing is they're using a full wave bridge. It looks like it's being used as a bridge rectifier, but it's not. It's two center tap full wave power supply. And of course, here's our filter. What's this right here? This is a regulator. It's what we call a fixed regulator. So 7812, it's a 12 volt positive regulator. The 79 series, these are negative regulators. These are very, very popular. They're 1 amp regulators. 7812 would give us 12 volts regulated. 7912 would give us minus 12 volts regulated. These are the LEDs that turn on when you turn on your trainer. These right here, these are LM337s. These are variable regulators that we'll look at later on. So these are fixed regulators. So these guys are going to give you what? They're going to give you a voltage. A variable regulator is going to give you a voltage that you select, right? So the here's the 317 that's giving you your negative output adjustable. This is your 317 that's giving you positive. This is a 5 amp 5 volt regulator right here. It's an LM 7805 that we're popping left and right. So we're converting this over to an LM 723, which is it's a 5 volt 5 amp. Another one that we're moving over when they go out. So this is what we're working on here. This is what we're going to go to the labs and we're going to start working on these guys. We're going to do a half wave rectifier. Then we're going to do a full wave center tap. Then we're going to do a full wave bridge. We need to make sure that hopefully this symbol right here is wrong. Because if that symbol's right, we can't use the trainer for the full wave bridge. And why is that? Because the common can't be on the transformer, it's got to be on the other side of the diode. Y'all understand? So when I set the common up here, here's the transformer. As I switch back over to my camera. So here's my transformer, here's my common. So my common is on the other side of the diode. So if they put that ground on the transformer side, then we can't use this for full wave center. Well, we could, but we just gotta, well, we couldn't look at it with an oscilloscope. Because this black lead on the oscilloscope, this is ground, right? You understand? So if that means if they reference that transformer to ground, then we could hook up the full wave center tap across both outputs, but we couldn't use an oscilloscope to look at the output. And we're going to be looking at oscilloscopes. If you haven't worked with an oscilloscope before, then let me know and I'll tell y'all it's not a meter. So a meter, what's the black lead on a meter? Is that common? Is that circuit common? On a meter? Is the black lead a circuit common? Yes or no? Is the black lead on a meter circuit common? Yes or no? Well, if it was, I couldn't hook it anywhere I wanted to in a circuit. The black on a meter has nothing to do with the common of the circuit. It's the meter common. It's what you're making your measurements relative to a meter. So that means you can take the black lead of a meter and you can put it anywhere you want to. If that meter was circuit common, that means if I put it in the center, I would short out half my circuit. Y'all understand what I'm saying? Yes or no? This is very, very, is this important? This is very important. So that is not, that black lead on that meter is not circuit common. It's just a black lead. It's a reference to what the meter shows as being negative and what's the meter. In AC, it means nothing. Your black lead on AC means nothing. Means nothing. Y'all understand that? The only time it comes into play is when you check diodes. Why? Because you have to put the black lead. So that means that polarity means that. But besides for that, it means nothing. Checking P-N junctions is where the black lead really comes into place. Or measuring DC. And DC is not, if you understand electronics, and you understand that if you measure a negative or you're supposed to measure a positive, there's a 99.9% of the chance you just got your meter leads reversed. In the old days, it really mattered, I said, when we had a pointer meter, because you could peg your meter out in the negative direction. So on your old meters, on your analog meters, you got to really be cognitive when you measure DC where that black lead is, because you can screw your meter up. But on digital meters, they don't care. All it does on DC is give you the wrong polarity. So the problem is that if we get into a circuit, and this is extremely important, if you get into a circuit that runs that has ground on it, so let's say it's an AC circuit, and this is common or ground, and then I come over here and just put some resistors. Now, if that black lead on your meter was common, if I came over and put my black lead right there, I would be putting a common right there. And I've just shorted out these two resistors right here, right? Y'all understand? So the black lead on a meter is not common. Some people call it meter common, but it has nothing to do with circuit common. So what can I do with a meter if I wanted to measure the voltage drop across that resistor? I can just put it across that resistor. If it's AC, which side does the black lead have to go to? I don't make any difference. AC has no polarity. We got a animated GIF somewhere I need to bring up where they show you 60 cycles and they're changing the plus minus sign at 60 cycles. And to us it looks like a cross, right? You understand? Because why? Because they're changing so fast. And 50 cycles is, 60 cycles is 10 times more. If I come over here and my circuit is referenced to ground, and we run into that a lot, that black lead on on my oscilloscope is referenced to ground. So it means if I take my black lead and put it right there, if I take my black lead and put it right here, what I've done is I put ground on that side and I've just shorted out my power supply. And this is what one of our students did this, doing these power supply labs for this class, by the way. Tried to put two grounds into a circuit. He was going to measure across the source, put the ground at the top, put it on the bottom, and then as soon as he did that, he did what? Shorted out. Y'all understand why, right? So on an oscilloscope, the black lead is ground. Well, it's not. On this, it's black lead. We're not letting y'all use regular oscilloscopes. Oscilloscope probes run around $50. So this is an oscilloscope. This is actually an oscilloscope probe right here. So you'll get these when you buy your oscilloscope. This guy right here is ground. We used to teach a nice class here and had an SCR package. And there's no telling how many of these below grounds that just disintegrate. Because they tried to do what? They tried to measure across an SCR. You can't do that. So this is ground, and this is your scope. Normally it comes with several leads. We like to use this one. It's got a what? It's got a little fish hook on it. We come up here and pull this off. This right here is ground. What they're doing is they're shielding the whole scope probe so it don't pick up a lot of electromagnetic interference. So they bring the ground all the way out to the very tip. So it means if I come up here and start probing around in here, and I accidentally touch that metal right there against one of these diodes, what did I just create? Short circuit. So what they do is they come with these little caps. Comes with a little pack that gets lost, that anytime you're going to use this, and this is real nice because this is a nice little sharp thing, so a lot of times when we probe with this. But if I come up here and probe with this right now, what I need to do is find one of them little caps and do what? Cover up that ground. If I can't find that cap, then don't probe like this with a scope probe. What you can do is get you just a piece of black tape and do what? Put it around that ground. Y'all understand that? That's ground right there. But remember to take it off or you're going to screw up this guy when you slide it back on. That's happened before. But they leave the tape on there and try to slide the cap on. So what's nice about this, if we come up, so if I was to take this scope ground right here and hook it right there, what did I just do? I shorted out my transformer, right? You understand that? So that means on scopes, all these grounds have to be at the same spot. And I'll try to show y'all how you can use two probes like a meter, but don't just go moving these grounds. So once if the trainer's got a ground reference, you have to use the trainer's reference. Everybody understand that? You cannot reestablish another ground inside the circuit. So you got to be real careful with the scope. This function generator is grounded. So that means if I was to hook up my scope backwards to this thing, I would short my function generator out. Now this guy's got a 50 ohm resistor on the output, so it should be okay for that reason. Well, that's not it. It's for something called impedance matching. So when you start using the oscilloscope, and this is what we're talking about. So for the full wave bridge, if the center tap on that full wave bridge is grounded, then when we do the full wave bridge, we're going to have to get one of these 12.6 volt transformers like this. And we got them in a box in there. They're fused. So we have the secondary fused. So they're fused. Are we okay? So it'll be a while before you get there. I'll put out, and all we do is have to take out an ohm meter and see if the transformer's grounded. According to the schematic, it is, right? But the schematics, we'll find out real fast that commons and grounds are one of the most misused symbols in the electrical or electronic trade. They'll draw a ground symbol out there on your car, and your car doesn't have ground, right? But y'all understand the difference between a ground and a common? What's a ground? What's a ground reference to? Earth ground. Yeah. And then a common is just a reference. It's the reference for a circuit, right? Y'all understand this? A lot of times a common and a ground is the same. A lot of times they're not. A lot of times it's impossible to have a ground, like in your car. Your car cannot be grounded, right? Your cell phone cannot be grounded. This computer right here is not grounded. Are we okay? Okay, make sure I give you this out. 1, 2, 3, 4, 5. Who's not here? Huh? These are worksheets. This will be due. These will be due Thursday night. Got a good Labor Day. And what we've got is we got a half wave rectifier. We have a full wide center tap rectifier, and we have a full wave bridge rectifier. And what does it say y'all need to solve for? Average DC output. Alright. We talked about ripple frequency. I think ripple frequency on there, or pulsate. Why we need to know the frequency of the pulsating frequency. So I'm plugging this in Alabama Power. What's Alabama Power's frequency? 60 hertz. What's the frequency of these pulses right here? What's the frequency of these pulses? No, they're not 60. Because what happens, they're what? So what happens, and why you need to know this, later on when we filter them, it's one way that we tell if we got a defective diode. But another reason, of course, is when we calculate the size of the capacitor we need. So what I'm doing is I'm taking this, which is a cycle, y'all understand, and I'm converting it into this. Now, what is the definition of a cycle? That's one repetition of a repetitive waveform. So how many repetitions do I have here? That's 1 watt. 2, how many do I have down here? I have 1. So that means on a full wave rectifier, it's going to be twice your input frequency. So the period here is the 16.7 milliseconds. The period here is 8.3 milliseconds. This is actually 16.66666. This is 8.3333. So notice the period is 1/2. So the frequency of a full wave, the output pulsating frequency of a full wave is twice the input frequency, no matter what it is. And we could verify that. We could set our scope up to measure frequency, or we could set it up to measure time for us. Well, let's measure time. I got it on 2.5 milliseconds per division. Now, what I'm going to do is change the position so I can line the pulse up to one of these lines. So that's 2.5 milliseconds per division. I have 1, 2, 3.24 divisions. 3.4 divisions times 2.5 milliseconds. What's that? Huh? It'll be greater than 6, because it's 2.5 milliseconds per division. What's that? It's actually 8.33, but you got to understand a scope is not extremely accurate. So it is 8.33. It's really 8.3 milliseconds, even though you got 8.5. Y'all understand that? Let me turn off panel 2. The problem with the oscilloscope is we're counting in ones. So that means there's five minor divisions, so each one of those is worth 0.2. Right? So one way we do on our oscilloscope is one way we can measure time is we can count the number of divisions and then multiply it times the value per division. Or you can count in 2s. It's hard to count in 2.5s. This scope's kind of strange in that it has a 2.5 division on the horizontal. Most standard analog scopes go in 1s, 2s, and 5s, which makes it real easy to just count, right? So this would be, if I count in 2.5s, this would be 2.5. This would be what? That would be 2.5. This would be 5. This would be 7.5. And then I'd have to figure out what these minor divisions are equal. They're not, it's not equal. So in this scope, it's just easier to do what? Count the number of divisions. But when you count your minor divisions, you're going to use 0.2, 0.4, 0.6, 0.8, right? And then do what? Take that and multiply it times this, and that'll tell you what you're measuring. So time is this way, voltage is that way. So what's my peak voltage? I'm going to do is bring it down, put it on line. So I have it on 5 volts per division. That's 5, 10, 15. Right? 5 volts per division. So each one of these is one division. 5, 10, 15, 1, 2, 3, 18 volts peak. So what DC should we measure? With my meter. And this is V peak out, by the way. This is V peak out. This is after the diode, so you don't have to subtract that 1.4 volts. Two V peak over pi. So 2 times 18 divided by 3.14. What's that? 7.5. Okay. Put my meter on DC, got it on 40 volts, turned it on. Put the meter up here. 11.2. Not too bad, is it? So that's our DC out. And what's peak? Peak is 18 volts. Now watch this. This is what we're going to work on later on. So this is a device we call a capacitor. I'm just going to come over and put it across these guys right here. Oops, where's my clip? Can't look at two things at one time. Wait a second. Okay, so what's my output voltage? What do you go to? Okay, what I'm going to do is switch it back over to this oscilloscope. So this is what? This is pulsating DC, right? You got to be careful with the polarity on these things. These things will blow up. That's DC. That's pulsating DC. That's DC. You'll see what we're working toward. Okay, so this right here is a filter that we'll look at later on. See that? Here's zero. So here's 0 volts right here. Right? You understand? So what we're seeing now is we're seeing pulsating DC. Now this is unregulated DC. This is not pulsating anymore because it never goes to 1. It never goes to 0. We'll size that. As you can see, we'll look at later on why it's important to know the ripple frequency and stuff like that. And we'll open these diodes. By the way, a little troubleshooting. What would happen on a half-wave rectifier if the diode opens? Right there. What would happen if that diode opens? What would happen to the output voltage? Pretty close to it. Once you've got AC in a circuit, it's real hard to get 0, but it's going to get way down there. It's going to go way down, right? And you're right. Your meter measured pretty dang close to 0. Okay. What would happen if this diode shorts? You're going to put AC across your load, which a resistor don't care, right? You understand? But if this was a solid state device, it could pop it real bad, right? Okay. All right. So this is pretty easy to figure out, right? When we get to a full wave bridge, what happens if this diode right here opens? You're going to turn a full wave into a what? Half wave. Your output voltage is going to be about half of what it's supposed to be if it's unfiltered. Now understand that? What happens if either one of these diodes short? You're going to get a blown fuse or burned wire. That is a short circuit, people. Y'all understand? If I come over here and I put I'll replace one of these with a straight piece of wire. As soon as this diode forward biases, here comes my current right there, right? You understand? So if you got one of your diodes in a full wave bridge, in a full wave center tap, if it shorts, that's a short circuit. Odds are it's going to get both your diodes. Hopefully you're going to be fused right. If you don't, it's probably going to burn your transformer up. Your transformer is going to start humming real bad. It's going to start smelling real bad. You need to turn that sucker off as soon as you can. Right? You understand? If you put in one of these diodes backwards, you got a short circuit. You understand that? What happens on a full wave bridge if you lose one of your diodes? Let's say this guy right here opens. No comments? So it's just, when it's open, it's just gone, right? Huh? Well, it's open. It's not shorted, it's open. Y'all understand between the open and the short, right? So that guy's right there is open. I'm trying to draw, but something's going on. Well, do we have a path? So when this is negative and this is positive, I can come up this way, I can go through that way, I can come up here, and I can go there, right? Understand? So that's one path. On this one right here, this guy right here is open. So this is negative and positive. I'm dead in the water. So in a full wave bridge, on a full wave, if you lose one of your diodes, it turns into a half wave. What would happen if one of these guys short? Well, the same thing happens before, right? Y'all understand? If one of your diodes short in a full wave bridge, you have a what? You have a short circuit. Everybody okay? And of course, how would you check that thing that I passed around? So what we got is we got this right here. And remember, our meter only has the ability to check one diode at a time. So we're going to check this with an ohm meter. Here's my AC. So these two are labeled what? AC. This right over here would be positive. This down here would be negative. But I don't have access to the diodes. All I've got access to 4 leads. So all this is encapsulated inside a So somebody help me out. So I'm going to check this with my ohm meter. But what I'm going to do is I'm going to check these two diodes first. I'm going to come over here and I'm going to put my black lead on the plus. Y'all understand that? And then I'm going to put my ohm meter right here. I'm going to set it up and put it on the diode scale. Y'all understand? Yes or no? And then what am I going to do? Then I'm going to put my red lead. And put my red lead here. Oops, that's supposed to be red, Rich. I'm going to put my red lead here. Now, which diode am I checking? I'm checking this diode, right? And then I'll move it down to here. And then I'll be checking what? I'll be checking that diode. So that's your two diodes. Understand? Okay. Then I'm going to move my meter and I'm going to put my red lead on the minus. So you put it on the opposite polarity of the DC's going back because you're going back over here, right? Then I'll make sure my meter's up here. And then what would I do? I'll take my black lead on my meter and I'll put it right here first. Don't make any difference. I'm going to be checking this one. Then I'll move it over to where? I'll move it up to the other AC. I will check the two diodes. So that's the way you check an integrated bridge. And you're going to run into these all the time. Okay, I got to forward bias these diodes. What do I need? Now, we're not talking about the source. We're talking about checking the diode. How do I forward bias that diode right there? What do I have to put on this side? There's the cathode. What do I need to put on this side? I need to put the negative, right? You understand? What do I need to put on this? I need to put the negative. So what lead is the black lead on my meter? It's the negative when I have it on the diode scale. Okay, now I've satisfied these two negatives on here. So I'm going to take my red lead, which is my positive. I'm going to touch this one labeled AC. And now I'm checking what? I'm checking this diode. I'm going to come on, and you're not really concerned if you're checking the diode on the left or the right, because if any one of them's bad, you just replace the whole thing. You replace the whole thing. Now what you got to understand is the bridge costs more than an individual diode, but it's cheaper than buying 4. So what that means is, and we run into this a lot, where they use these bridges because it's cheaper for them right off the bat instead of buying 4 individual diodes with this rating, but it's going to cost me more to fix them because I cannot replace a diode. So if I have 4 diodes in there and one of them goes out, and there are 4 independent diodes, I can check it the same way, or I can get to the diodes, right? You understand? And now I can replace a diode. It's going to cost me a lot less to replace one diode than it is the bridge. But the company that's building these things is not trying to look at how much it costs to repair them. They're looking at how much it costs to build them, right? You understand? So you're going to run into a lot of these integrated bridge rectifiers in these power supplies. So if I look at these power supplies inside this trainer, we'll look at the little integrated bridge rectifiers. So now you got to figure out how to check those things out with an ohmmeter. And what you do is you put the opposite polarity lead on. So if I'm checking the plus side, I put the what? I put the minus lead on the plus, and then I touch the 2 AC leads. Then I'll do what? Then I'll take my what? I'll take my red lead and put it on the minus, and I check the 2 AC leads. If all of them measure around 0.6 of a volt, then that means all your diodes are good. But also always reverse bias it too, because they could be leaky, right? You understand that? So when it's lit, when reverse bias, it should show the maximum reading. Forward bias, it should show you about what the VF is on the diode. If you use what? If you use the diode scale on your meter. So one thing, you got to look at your meter. So on this one, if I don't see a junction, this one shows me 3.124 volts. So it would show me about that when I reverse bias the diode. If it drops down to, you know, like 1 volt or something like that, that means the diode's leaky and it's bad. Now you need to do this out of circuit, right? You understand that? Or isolate one of your leads. Or here we'd have to isolate 2, because when you reverse bias them, you could be reading back through another device that's in parallel. You could read back on your load. So if you do it in circuit, odds are this right here won't measure the same. And let's do this. What I'm going to do is I'm going to kill the thing. Another problem we have is how much resistance does the transformer have? Does it have a lot of resistance, or does it have almost no resistance, right? So I'm going to unplug this. And so if I come over here and try to check this on my AC leads, we'll see if this works. Oops. So I've got my meter on my diode scale. I'm going to check it like it's so I'm going to come over here and I'm going to put my my red lead on the negative side, and then I'm going to come over here and touch my 2 ACs. Okay. Can you see that? So this is a silicon. Now I'm going to put my minus on the positive side and touch the 2 sides. And then, so I've checked I've checked all 4 diodes just by putting my meter in 2 different spots, right? But let's see if it checks the same. So this is reverse bias. So I'm going to check both sides. And it's still doing pretty good. But it won't surprise me because we're using a pretty good size. This is a 10K resistor. This is a 1K resistor. So sometimes when you reverse bias it, it might not show overload or whatever your meter shows. So what you need to do, and we reverse bias it the same way. So I would come over here and just put, so now I have my, so now here I have my positive toward my positive, and I'm going to touch the 2 AC lines. So what you need to do when you check these diodes is make sure not only do you, so it's not showing me 1.3, why is it showing me 1.2? I mean, it's not showing me 3 volts anymore. Why is it showing 1.2? So that's good when it's reverse bias. This is good. We know the diodes are good. but it appears to be leaky. Why? Because it's in the circuit. What I'm doing now is I'm looking at this 1K resistor over here, right? You understand? So what we're saying is that, you know, your reverse bias, when you reverse bias it in the circuit, odds are it's going to appear to be leaky when it's not, because it's seeing this resistor out there now, right? You understand that? If I come over here, just to prove that, okay, I'm going to come up here and pull out my resistor. See that? So that's what I'm saying. A lot of devices, if it checks good in circuit, we assume it's good. If it checks bad in circuit, you need to isolate it and check it again. And that's even true on resistors or any electronic component, because you're going to have these other devices in there in parallel, right? You understand that? And you're using an ohm meter. Your ohm meter all it looks at is what the source sees. So what happens is it's looking at the rest of it. It's looking at all the loads. You understand what I'm saying? So yeah, these diodes are fine, but they appear to be leaky because it's the meter's reading what? Through the resistor. Everybody understand that? So watch out for that. So that's why we check a bridge, even in circuit. So what you can do is you check it real fast. The other way, it would take you 4 different spots. You'd have to change your polarity each time. Right here, we just have to do it, you know, twice. We check 2 diodes, switch it around, check the other 2 diodes, and then flip them around, do the same thing, reverse bias. So these solid state devices, make sure you check them both directions. You need to check them for reverse bias and forward bias. Everybody understand that? So that's a full wave bridge. What's the advantage of a full wave bridge over a full wave center tap? Don't say more voltage, because I could go, you know, 12.6 transformer. You're right. If I used the same transformer for center tapped and load, I would get the same voltage. But if I went to a 30 volt transformer, center tapped, it would give me about the same. Uncenter tapped, right, or center tapped, would get about the same. Everybody understand that? So the advantage is not we get more voltage out of a full wave. That's not the advantage. What's the major advantage? Why do we have more full waves than we have? Well, predominantly probably full wave bridges than we do full wave. The trainer uses that. The cost of it is the dang transformer. A center tap transformer costs a lot more than an untapped transformer. Y'all understand that? So that's the only advantage of using a bridge. Diodes are a lot cheaper than transformers. Look up I don't know if I would have to look it up. A 6 point. So if I was going to get the same thing out, I could use a 6.3 volt untapped transformer and get the same thing that I do out of a 12.6 volt center tap transformer using. So when they start tapping those transformers, they have to bring another set of copper on there. They have to figure out the exact center or try to get it at the center. It's never at the center, but it's pretty close. So tap transformers cost more. Just like the transformer for the trainer is not cheap. $20 for that transformer. And why? Because it's multi-winding, and then 2 of the windings are center tap. So let's pop open one of the trainers and look at our power supplies. We could do it now, or we could wait. Let's wait until we get through with regulators. But they use the little bridges. These guys here, I don't know what these are rated out. I have the one that I passed around. The one in the trainer is a little small. But there's what, 4 of them in there? This is the transformer right here. And it look, according to this is our 12 point, and it's kind of labeled wrong. This is what we call a 12.6 volt center tap transformer. The trainer rates this as 6.3 volts and 6.3 volts, and they call this 0 volts. It's actually a 12.6 volt transformer, because when they rate the center tap transformer, they rate it all the way across the outsides. You understand that? Looks like it's isolated, but what I'll do is I'll take an ohm meter. All we have to do is just take an ohm meter, put it on this, go over here to this ground lead on the trainer, and we should measure pretty close to infinity. If it measures infinity, then we're fine. If it measures 0, then that means we can't use this. But I was showing y'all the wrong transformer. This is the transformer right here we're going to use. But if you want to use one of these, that's fine too. If you want to actually use one of the transformers, don't use the trainer transformer for this. Are we okay? Alright, so what we're going to do? Yeah, we're going to go, some of y'all are still working on your diode lab. You need to finish that up. Then as soon as you finish that, you can go into the rectifier lab. Which lab number is that? My lab book and y'all's lab books don't match. Written on the side what the lab number is. So your rectifier labs, let's see. Rectifier lab is lab 32. It's the same as local, right? Y'all's is 32. And of course, if we look at lab 32, let's look over lab 32 and see if y'all got any questions. And there are some corrections to the lab book y'all are going to have to make. Huh? Well, let's get through with this, and then not unless you got to go right now. You okay? Well, we'll fix the other lab. Y'all go ahead and take a break. That's fine. And then we'll go over this when y'all get back. So y'all go ahead and take a break. Rectifiers. Lab 32. And my camera's upside. I'm trying to figure out how to get my camera to show right. Here's where they misuse a symbol. So we are not going to use the black ground lead on the trainer. Y'all understand that? We're going to use this isolated transformer. We'll establish a ground with our scope rope. Everybody understand that? So this is not a ground. You need to change this symbol right here to the symbol of a comma. Y'all understand that? So that way we're going to draw a chart. We're going to do the secondary. What you need to do is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Try to get one cycle on this as close as you can. Everybody okay? So this is secondary. This is going to be AC. This is V across the load. That's going to be your DC. So this is going to be your pulsating DC. We're going to use a 1N4001, which I think has a PIV rating of around 50 volts. Then we're going to do calculating. We're going to compute before we measure. Because if you don't know how to compute it, then you don't need to measure, right? You understand that? So here, this says what? It says VP, but so you're going to mark that out. We're not using VP. We're going to compute V across the load, right? You understand that. And then we're going to do what? We're going to measure. Okay, everybody understand that? Your computed is going to be using that 2.6 volt transformer, even though I showed y'all the way they got it labeled. 6.3 center, 6.3, it's actually a 2.6, 12.6 volt transformer. And we're going to use it all the way across that's what that says right there. Sorry. So So this is the way the trainer has that label. They got 6.30, 6.3. Of course, it's a 12.6 volt transformer, so we're going to use it all the way across. And I'm pretty sure it has an isolated center right. So that's only 0 if you measure it relative, if you make it 0, right? You understand? So if I put my black lead on my meter here and put that, it's still going to measure 6.3. So we don't have to worry about what lead we make common. So, you know, we could do the half wave across here if we wanted to, but we're going to do it all the way across right there. Everybody okay so far? What we're going to do right here, can y'all see what this says? We're going to put in a what? Filter capacitor. And it says we need 100 microfarad. I was using a 40.47 microfarad a while ago. So the storage capabilities of a capacitor. So a capacitor works kind of like a little tiny battery that we can charge up, and then we can discharge. But it discharges real fast. But we're dealing with milliseconds here, right? You understand that? So let's look at those formulas real quick. So as soon as we hook up as soon as you hook up a capacitor, this 2V peak over the pi is gone. Y'all understand that? That is not the formula we use. Y'all understand that? So what we end up with when we hook up our capacitor is we end up with a, let me put it in there permanent. Where's my First of all, the capacitors we're using are polarized capacitors. What do you think that means? Yeah, if you hook these suckers up backwards, they will pop on. So before you put power on any circuit, it says up here, it says, have the instructor check before applying power. Because we can burn up some trainers here if we don't hook these things up right. Everybody understand that? When we hook up these capacitors, these guys are polarized. That means if you hook them up backwards, they're going to pop on. So when they get on these capacitors, they identify one of the leads. We call this a radial lead. We call this an actual lead capacitor. So we have two types. We have what they call radial lead. This is not a capacitor, but this is a radial lead device. So radial lead means the leads come out one side. Actual leads, they come out two sides. It's easy to remember because this kind of looks like a car axle, right? And they're going to identify one of the leads. They don't identify, well, it depends. They're going to identify at least one of the leads. They're either going to identify the positive or they're going to identify the negative. And you'll see this big old negative sign as soon as it focuses right here. It's going to focus. Come on, focus, camera. See it? So that means this lead right here is negative. So this lead right here has to be what? Positive. Before I hook my power, where's my power supply? So if I want to hook this across my load, that's where we're going to hook it at. This is our negative. Sorry, guys. This is our negative. This is our positive. So I'm going to hook this thing here like this. There's negative. There's positive. Are we okay? And then we turn it on. Of course, we don't have on switches. You have on and off switches on the trainer. That's one thing nice about using the trainer. You can turn it off and on. If you would use one of these transformers, you're going to have to do what? Yeah, unswitch it. That's what we call unregulated. Oops. And I'll get my trigger line up in there and synchronize this. No, I thought it was. set up right. Of course, this little line right here, this shows you my zero, so we lose our pulsating DC. Now, the capacitor charges up to peak, and then it discharges down through the load. So that means the only difference between the peak voltage and my output voltage is what we refer to as ripple. And what would be the average DC value of that ripple voltage? Let me turn it up. It's an alarm that tells us this. So by the way, when I turn my scope up, when I try to see the ripple voltage, where did it go? So I'm going to turn my voltage per division. So there it is. But when in my zero, it's set here. So when I try to measure my ripple voltage and I turn it like that, where's it at now? Okay, so what do I need to do? Then if I turned it again, I would have the same problem. We got different ways that we can bring the AC in. One way we can bring it in is, and this is not exactly the way it is. And if anybody that's had AC should know what's going on here. If you hadn't had AC, and just what happens is we have this device right here. So one way, we have three ways we can bring in the input. So most scopes have a switch on it, so I'll draw it as a switch. We got one where we can bring it straight in into the amplifier circuits. We got one, if we switch it right here, that's not right. Let me swap this around. I'm going to put my pole on this side. So we got one position we can put the switch in, and we'll bring that straight in. The other position, if we put it in, it's going to go through a device called a capacitor. And when we switch it to this other one, I'm not going to show you that. That's a little harder to draw. So what happens is that and we call this DC for direct couple. And then this one down here is labeled AC. Which is kind of misleading. So if I want to measure AC, what would I put it on? I put it on direct couple. So 99.9% of the time we use direct couple. Now, what a capacitor will do, one of the main features of a capacitor, it'll pass AC and it will block DC. So if I want to block DC, I put it on the AC. I put it on AC couple. If I don't want it to block DC, I put it on direct couple. That makes sense. So what I'm going to do is I'm going to come over here and I'm going to put I want to block the DC component of this thing. So let's go back here. I want to block the DC component. I want to block the DC, but I want that AC component to pass through. That's an AC component riding on DC. Okay. So I'm going to come over here on my input on channel 1, and one of the things we got right here, y'all can see, it's got DC, that's what? Direct couple. I'm going to change it over to AC, and notice, can you see what happened? It dropped down to my 0 volt reference. Now that I take the DC away, no, it's there. I just told my scope to block. Now what I can do is I can put this sucker into the center, and I can start turning this thing down, and I can measure that ripple voltage as accurately as I need to measure. So this is actually what's going on. 120 cycles a second. Now this is VP, so this is when the capacitor charges up, and then the capacitor is running the load down through here. Now, there's a formula that we'll talk about later on that it's called an RC time constant, and the formula I'm going to show you is the derivative of that formula. Substitution, substituting on the law.
You will adjust the slope. You will adjust the slope. You saw around AC rating. You need to go to the 4 length.
Well, when we're looking at these, what we need to do is when we measure the scope, it's just like the analogy I use, or analogy I use is when, if I was to get in my car, and they could do this, right? You understand? And I come over here, and let's say if I on my odometer, on my speedometer, on my car, right here was 0 miles per hour, and then right beside it, right over here was 120, and it's somewhere in the center. How fast are you going? So what do? Well, they spread it out. So your scope is the most accurate when you make the waveform as big as you can make it without it going off the screen. And the problem is the lab will tell you to set it here, and then they don't tell you to rechange it, and people's trying to measure this stuff, and they got it looking at something that big, and they need to do what? When they make it as big as they possibly can make it. So what we need to do on the scope is we need to turn these controls until I make it as big as I can make it. So that right there, I can't, that's no good. Why? Because I'm off my screen, right? You understand? So I'm gonna add more volts per division, and of course that right there is too small, right? You understand that? The problem is if I leave it on DC and try to turn it down, it does what? It's looking at the DC and it goes off the top of the screen. And your position controls can't even get it back to you anymore. But here, when we put it on the AC, what does it do? When I put it on AC, what do we use the AC coupling on the scope for? We use it for one thing, quad DC. And the problem is you get people that try to relate an oscilloscope to a meter, and they think by George, when you measure AC, you're supposed to put it on what? AC, and when you measure DC, you're supposed to put it on DC. Well, this whole dang time, I've been having my scope on direct couple, and it measures AC just perfect, right? You understand that? So the only time because it'll change, that capacitor will change signals, so you don't need to put it on. So what I can do now is I can come up here and I can measure that value of that. So that capacitor charges up the V peak. That's V peak right there. And then it discharges, and then then it charges up again on the next V peak. So where's my DC going to average this at? At the top, at the bottom, or right down the center? Right down the center. So my DC average will be right down the center of this. Y'all understand that? It's just like AC. So the average value of a DC wave, the average DC value of a sine wave is 0, but that's in the center. So what we're saying is that now I've moved my average value down to the center of this, right? You understand that? So that means if I can calculate this, then I can take 1/2 of that and subtract it from V peak out, and that'll give me my output. So let's look at our formula sheet real quick. VRPP, V ripple peak P. So y'all see the formulas for V ripple peak P? And we'll get into more of this later on. The book is going to have y'all compute these. And if you can't calculate it, you don't need to measure it. Everybody understand that why? And you'll understand what's going on. I'm going to put it back on DC. I'm going to put my volts per division back down here. I'm going to come up here and reset my ground reference down to here. I'm going to put my scope on DC coupled again. How do I do that? I go to the channel I'm on, go to what? Coupling, hit this, go back to DC. And normally when we measure DC, we put our scope down all the way at the bottom. That way we get more volts per division. So see, I can't go there. I can go there. So what does it say the formula is for calculating my ripple volts? That's not 1, that's I. Yeah. Should be an uppercase I. Oh, dang it. Are y'all looking at the formula? So V ripple peak peak is equal to I the load over F times C. Where am I going to get the F? This is full wave. I'm putting 60 cycle in, so what's my frequency going to be? It's going to be 120 as a full wave. Or if you use the other formula, you'd have to use 8.3 milliseconds. What I like about this formula is if you know the frequency of the pulsating, you just stick that in. This will be the size of the capacitor. I'm using a 47 microfarad. So what do I need to know now? I need to out of the load. Y'all okay? Yes or no? You okay with it? So I need to know out of the load. How am I going to get out of the load? So what I have is I have a full wave bridge, right? We have a positive supply. We have a 1K ohm resistor right here, right? Then we have AC hooked over here. This is 1K ohm. What we're going to do is we're going to guesstimate. Well, it's a valid guesstimation. But what I'm going to do is I'm going to say I of the load is equal to approximately, it's actually going to be less, V peak over 1K. Because the only difference between my output voltage and my actual DC voltage is right there. So what we're going to use is we're going to use that right there. Which means our output will probably be a little less than what it actually is, but this gives us a real good approximation. What's VP going to be? Somebody help me. So V peak is going to be equal to, we're using a 12.6 volt transformer. And I'm going to divide that by 0.707. That's going to give me VP. Now this is an approximation too, because we're saying the transformer is exactly 12.6. What's the odds of it being exactly 12.6? Slim to none, right? But it's going to be what? It's going to be close enough so we know if it's right, if it's working or not working. So what's VP? What's that? 17.8. We'll calculate V peak out, which is going to be 17.8 minus 1.4. Why 1.4? Yeah, it's a full wave bridge, 2 diodes, right? You understand. What we're going to have? What's that? 16.4. I'm going to approximate my current. Out of the load is going to be equal to 16.4 divided by 1K, which is going to be 16.4 milliamps. I'm going to come in here and plug that into this formula right here. 16.4 milli. That's not, it's going to be milli. We don't put the units in this formula, right? Because they won't cancel each other out. So what's my approximate V ripple? Nobody got it? 2.9 volts. About 2.9 volts. So my output voltage is going to be, the DC output should be about 16.4 minus 2.9 divided by 2. Y'all understand that? Because the average, we calculated peak to peak, but it's going to average right down the center. So what should my output voltage be? Approximately what?
14 or 15 roughly.
And of course we're measuring 16.8. So you'll see my measurement. Calculate what? 15 point?
It's 14.95.
Okay, so we calculate 15 volts, measuring 16.8. Is that good or bad? It's definitely good. I mean, first of all, we use 12.6 to calculate it. If I look at the actual peak-to-peak value, it's going to be more. We did calculate what for our ripple? 2.9 volts. Let's see what it actually is. I'm going to put it back on DC coupling. I'm sorry, AC coupling. Then I'm going to shift my ground up. That's the best we can do, right? Move it down on the line. Got it on a half a volt per division. There's 1 volt, there's 2 volts, right? 2.1, 2, 3, 4. We got 2.4. We calculate what? 2.9. And that was a rough get because we use VP, right? You understand? But it's actually in the center, but it's going to be close enough. The output of our transformer is not 12.6. It's probably high because we don't have this thing loaded to its nearest capacity. We look at our output of our transformer, which we can't do, but we can look at the RMS value. So I'm going to put this across my transformer. My meter's reading 0. What's my problem? I got it on DC. This is a standard problem people have, right? Put it over on AC. It's measuring 14 volts. Supposed to be measuring 12.6, right? You understand? So that's the problem with our calculation. If we was to recalculate that using 14 volts instead of 12.6, we would find out that our output's going to be the same. But you got to understand that 12.6 is at a certain current, right? You understand? This is a 1 amp transformer. We're not even getting close to that. We're only getting 16 milliamps. So the transformer is barely even loaded. So the output's going to be a little high, right? You understand that? Because there's an R component to a transformer, right? You understand that? But we're close enough. The problem is, though, is I might take this one and plug it in at your house, and your input voltage is going to be different. So in that, instead of measuring 14 volts RMS, you might measure 13, right? Or it might be 15 volts, and that would still be, my calculator would still be in a real close range of what I actually measured. So this is what y'all going to have to do. Do y'all see how to do that? If you need any help on that, I'll help you, because we haven't covered that in class yet. What's going on, what the formula comes on, that will be our next lecture. But what we're going to do here for these power supplies is we're going to hook up a filter capacitor, 100 microfarad. This means it's going to have less ripple. We're going to be using a 2.2K resistor, so the ripple is going to be hardly any. I'm using a 1K, right? Then we're going to come up here and hook up a full wave center tap. And then here's the chart for that. and then we're going to hook up a what? Full-way bridge, and we're not going to use the center tap. We're going to use the center tap transformer, so we're not going to change it. We're just not going to hook up the center tap. Don't take the output of the transformer and hook it to the ground of your trainer. You're going to have to run that wire, right? You understand? Everybody understand that? If you hook it up to that ground of that trainer and you hook up your oscilloscope wrong, it's going to do what? Probably burn the trainer up, because they fuse it. They fuse it for all those transformers being used. All those secondaries being used. That means odds are we've had that happen. We've lost 3 transformers so far. I'm not going to tell you how many 5-volt regulators we've got. Okay? All right, gang, let's go left. By the way, I think we got one person in this class that's signed up for that texting application. You did? Okay. I need to go look. I mean, it's a neat deal to me. Huh? Well, there's only one teacher that I know of that's using it.